Can you see my slide?
Yes.
Okay, good. Okay.
Okay, we take about 5 seconds to set up the YouTube live streaming. Okay, we're good now.
Okay, hello everyone. So welcome to today's CFSM seminar. So today it is our great pleasure to have Dr. Tongqing Lu from Xi'an Jiaotong University to join us and give us a talk regarding his research on the fatigue of tough hydrogel. So Professor Tongqing Lu is a professor at Department of Engineering Mechanics in Xi'an Jiaotong University, China. He received his bachelor and a PhD degree from Xi'an Jiaotong University as well. He studied at Harvard from 2010 to 2012. And Dr. Lu is currently working on the mechanics of soft metals, including dielectric elastomers, hydrogels, and their applications. He has published more than 60 journal papers on PNAS, matter, GMPS, EML, etc. So with that, let's welcome our today's speaker. And Tongqing, now you can, the floor is yours. Please feel free to get started.
Okay, thank you very much. Thank you, Joanne, for the introduction, and thank Dr. Lee for the invitation, give me the opportunity to share my recent research in my group. So I'm Tongqing Lu from Xi'an Jiaotong University, China. So today my topic is fatigue of tough hydrogels. So maybe many people are familiar with the hydrogel. Basically, it's a combination of water molecules and polymer network. And it has the solid state, but also it can transport the water molecules. So many common examples of hydrogels, like the food or the plants and animals, the tissue. Yeah, so many existing examples. But all these examples, we can see the hydrogels are very brittle, cannot bear the large force or large load. So in 2003, there is a pioneering work, Professor Gong from Japan. So their group invented the first tough hydrogels, and we call it double network hydrogel, and we named it Gong's gel. So this picture shows that this is a single network hydrogel. So this hydrogel consists of a PEM, polymer network, and water molecules. So this is the ordinary hydrogel. You can see if you use a knife to cut it, and easy to cut it into two pieces, two halves. So, but the combined two polymer network together, and you can see the mechanical property has been greatly enhanced, and you can see I use a knife to cut it, and it can recover. So now we have already understood the mechanism of the high strength or high toughness of this kind of double network hydrogel. So this is a mechanism. So we believe that there's two networks. The red network is a long polymer chain network, and the blue one is a short chain network, is a PEM-PS network. So when you stretch this double network hydrogels, the short network will first break and dissipate energy as heat. So that's the origin of the high toughness. So we call it sacrificial bonds break. So this is the first generation of tough hydrogels. And after about 10 years, in 2012, Professor Zhigang Suo from Harvard University, they invented another type of tough hydrogels. There's also a double network hydrogel. So one network is the same as the Gong's gel, is a PEM hydrogel. And the other network is an ionic network, is calcium alginate. And they combine these two networks and form a hydrogels. And this hydrogel also has very high toughness. And we believe this also attributes to the sacrificial bonds breaking. So we can see the stress strain curve of this double network hydrogel. So here is the PM hydrogel, this one, and here is this one. So this is two single network hydrogel. If you combine these two networks together, you can see the mechanical properties have been greatly enhanced. So here we can measure the toughness of this hydrogel. This is the common practice in fracture mechanics. So we first stretch this material. You can see it can stretch 21 times without any pre-cut crack. If you made a crack, for example, in the middle, it can still stretch to about 17 times. And we can calculate the toughness of this hydrogel is about 9,000 joule per meter square. So this number is similar to that of natural rubber. So you can see this is a hydrogel with 19% of water, but its mechanical toughness is very similar to natural rubber. So then invention has greatly accelerated the application of hydrogels. So after that, many different kinds of tough hydrogels have been synthesized from many different groups and with many different technologies. And this new material has greatly broadened the application of hydrogels. For example, in this review paper, the authors claim that hydrogel material is the best candidate to bridge the biology and electronics, and some applications in this field, like some stretchable electronics, stretchable ionotronics devices. And another important application is in the the biomedical field, like the tissue replacement or the wound dressing. Okay, so we can see in all these applications with the tough hydrogels. So the fatigue of the hydrogels is very important because in these applications they are under prolonged mechanical loads. So that's why we want to study the fatigue of tough hydrogels. Okay, so in mechanics, we have two standard ways to characterize fatigue. So the first way is we prepare a sample without any crack, and we load it with cyclic loaded with a given stretch or given stress, and measure the lifetime, the number of cycle to rupture. Okay, the other way is we make a cut in the sample and apply a load, and we represent the load with we call energy release rate. And we measure the cut growth per cycle. So we cyclically load it and we record how fast the cut will grow and record this curve. So in this talk, we will use this method to characterize fatigue. And in this method, we have two material properties. One is toughness, means if you stretch it one time, it breaks, you get a number of toughness. The number of critical energy release rate called toughness. And another material property is called threshold, means below this critical energy release rate, no matter how long you apply how many times you apply cyclic load, the crack does not grow. Okay, so the study on the topic of fatigue of hydrogels has a very short history. So we know for mechanical engineering, for metal, polymer, composite, the study on the fatigue of these materials has a very long history, and until today is still a very hot topic because it's very important applications. But for hydrogels, the first paper is from my colleague, Dr. Tang and Professor Zhigang Su in 2017, actually, only about 5 years history. So the method is similar. Just apply a cyclic load and record the crack growth. So in this original paper, they have the first hypothesis, because the hydrogel they test is a very purely elastic material. So their hypothesis is that this material may be fatigue-free. Okay, but their experimental result is that this hydrogel also suffers fatigue. When we see a material suffers fatigue, we mean the toughness is much larger than the threshold. Means if you stretch it, the toughness is about 100 joule per meter. But if you load it cyclically, the fatigue threshold is only about 10. Okay. So now we proceed to study the fatigue of tough hydrogels. Because the tough hydrogels, as I introduced, the two typical kinds of tough hydrogels, we have the sacrificial bonds. And these sacrificial bonds are irreversible. So we have a simple prediction that, of course, the tough hydrogel may greatly suffer fatigue. So to verify this hypothesis, we tested the fatigue of tough hydrogels. So the first paper to test the tough hydrogels is from Dr. Bai in 2017. They prepared this source gel, and you can see the stress strain curve. Loaded and loaded is a very large hysteresis, means it suffers fatigue. And if you measure the fatigue threshold, the fatigue threshold of the tough hydrogels is about 50. So much smaller than its toughness. Yeah. So it's as we had predicted. Yeah. So our group, we first studied the fatigue of Gong's gel. Gong's gel is the first generation of the tough hydrogel. It's more famous actually. So the hypothesis is the same, because in these double net hydrogels, they're also sacrificial bonds. So the stress strain curve, we can see the first cycle have a large hysteresis. So greatly suffers fatigue. And we also measure the fatigue threshold of Gong's gel. We find that the fatigue threshold about 400. So the fatigue threshold is smaller than its toughness, about 3,000, but the number itself is still very big. So, okay, so this picture describes how we do the experiments. Actually, if you are familiar with fracture mechanics, it's a very common practice. You just make a pre-cut and load it cyclically and measure the crack growth. This is the number of cycle, this is the extension of crack. Okay, and after you, then you can plot the horizontal axis as energy release rate, and the vertical axis is the extension of crack per cycle. So then you can find the fatigue threshold. In this experiment, actually, we have a variable of the material. We have the concentration of the first network, but we can see this variable actually does not affect the number of the value of the fatigue threshold. Okay, so but we found we think it's an interesting finding if we compare these two kinds of tough hydrogels. So this is the first generation of a tough hydrogel. We call it Gong gel. Its toughness is about 3,000, but its fatigue threshold is 400. And this kind of hydrogel, the toughness actually is larger, but the fatigue threshold actually is smaller. So now we have questions. So what determines the fatigue threshold of the double net hydrogels? So now we look back to the literature and find to describe the fatigue of rubber. Actually, there's a famous model called Lake-Thomas model. So this model assume that if a fatigue crack grows, actually it breaks a layer of polymer chains in a layer of polymer chains, actually the energy to break the layer of polymer chains can be easily estimated. So alpha, this is energy to break a layer of polymer chains. Alpha is a prefactor. L is the length of the repeating unit, means the length of the polymer chain. Because of course the polymer chain has many carbon bonds, so we call the length of repeating units. So N is the number of repeating unit, and phi is here, and the G over V is the bond energy per unit volume. So L times N times G over V actually is the energy to break a layer of polymer chains. So here this N has a factor of to the power of 1 over 2, 0.5. There's a theoretical derivation. Okay, so this is the traditional Lake-Thomas model to predict the fatigue threshold of rubber. So now we just modify this Lick-Thomas model to account for to account for the tough hydrogels. So in the tough hydrogels, first we have two networks. So when the fatigue crack grows, we assume that all the short network, means the PAMPS network, have already broken. So and this network does not contribute to the fatigue threshold of this double network hydrogels. So the only modification is the water content. So Phi is the polymer fraction, because hydrogel compared to rubber, it has water inside. So you need to introduce the polymer fraction. So all the other part we can see is basically the same. But here, N means the length of the number of repeating unit, or we call it simply call it the chain length, is the chain length of the long network, or the chain length of the PEM network. So that's our assumption. So next, we just do some experiment to verify this assumption. So now we have a hypothesis that the fatigue threshold of the tough hydrogels will follow this theoretical prediction. So the first prediction, or our first assumption is that the sacrificial bonds do not contribute to the fatigue threshold. To verify this, we prepare two kinds of hydrogels. One kind of hydrogel is we call it tough hydrogel with sacrificial bonds, because we introduce this calcium bond. The calcium bond can cross-link these red chains to these double network hydrogels. When you stretch this, when you break these hydrogels, these sacrificial bonds will dissipate energy. So as a comparison, we prepare another hydrogel without sacrificial bonds. So here we use sodium. So sodium cannot cross-link these polymer chains. But these two kinds of hydrogels, the only difference is about the calcium or sodium ions. So the results is as I predicted. So the horizontal axis still the energy release rate, and the vertical axis is the energy extension of crack per cycle. So there's two numbers. One is toughness, the other is fatigue threshold. So the red one is the tough hydrogel, and the blue one is the ordinary hydrogel. So we can see the toughness of the double net hydrogel is almost 20 times the toughness of the ordinary hydrogel. But we can see the fatigue threshold is only 2 times difference. So it's as I predicted, the sacrificial bonds will greatly increase the toughness, but contribute little to the fatigue threshold. So that's our first verification. So the second verification is on the chain length, because L, G over V, if just the common bonds, all these are constant. The only the varying is the chain length. So this theory predicts that the fatigue threshold is proportional to the square root of the chain length of the primary network. To verify this, we prepare many different kinds of hydrogels with the same water content, but with different chain lengths, and measure the threshold of all these kinds of hydrogels. So we have 5 kinds of hydrogels with different chain lengths, and we can see the result that this is square root of the chain length. This is fatigue threshold. So it's the prediction and the experimental result agree very well. So these two kinds of experiments verify that. So our hypothesis, is correct. So now we can answer our question. So what determines the fatigue threshold? So actually the chain length of the primary network determines the fatigue threshold, and it follows this theoretical formula. So now we listed these two kinds of hydrogel again. The toughness is 300, and this is 3000, this is 9000. The fatigue threshold is 400, is 50. And we measure the chain length. Actually, in this paper, the chain length of the PEM hydrogel is about 50,000 repeating unit. And in this hydrogel, it's about 900. And we can see, this small formula predicts very well, explains why there's 8 times difference of the fatigue threshold. So after these experiments, we can confirm that the long chain strategy is very effective. Means if you want to improve the fatigue threshold of a double network hydrogel, you need to make the primary network, the chain length of the primary network very long. Then you can improve the fatigue threshold. But there's also a challenging issue if we want to use long chain hydrogels. Actually, this issue is not not only exists for hydrogels, but also for a wide class of rubber. So it's called stiffness threshold conflict. Yeah, if you look at a single network hydrogel or a single network elastomer, so the modulus is inversely proportional to the chain length. Means if the chain is very long, it's very soft. But the fatigue threshold is proportional to the square root of the chain length. So there's a conflict there. So actually many previous papers have studied this. They collected many data of different elastomer. This is a stiffness, this is a fatigue threshold, and we can see there's a conflict. There's a conflict. For network, for hydrogels, actually previously no people have studied this conflict. But of course, because it's the same, the only difference is just a polymer fraction difference. So how to resolve this conflict for hydrogels? And we found that actually in the design of this double network hydrogels, this conflict has already been resolved, because in this double network hydrogels, actually the modulus is determined by the short chain network, because the short chain network is very stiff, okay? But the fatigue threshold is determined by the long chain network. So these two material properties actually are decoupled in the double network hydrogels. So this conflict does not exist actually in double network hydrogels. So so we see the sacrificial bonds actually provides not only toughness, but also stiffness. And to verify this, we also prepared many different kinds of hydrogel. We only change the chain length of the long network, but to keep the short network as the same chain, as the same concentration. We can see the the green data and the star. So the stiffness is almost does not change, but the threshold can be improved about 1 order of magnitude. So so we can see the double network hydrogel design actually resolve this stiffness and the threshold conflict. After we confirm that this long chain strategy is very effective, actually now we can use this strategy to design some fatigue resistant material or fatigue resistant adhesion. So for example, there's 2 materials here we demonstrate with 2 pieces of cloth. So there's a interfacial crack here. So how to improve the fatigue resistance of this adhering of the interface? So as we demonstrate, very simple. We just introduce some polymer chains to interlock with the two pieces of cloth. As long as we use very long polymer chains, we believe that the fatigue threshold of this interface will be very high. So as we predicted, here's our result, experimental result. The horizontal axis is the polymer, the chain length. Now we prepare 4 kinds of adhering. Yeah, 4 kinds of PEM hydrogels as the interfacial adherent. So we measure the fatigue threshold of this interface. We can see it also follows this theoretical prediction, is proportional to the square root of the chain length. And we can see by simply increase the chain length of this hydrogel, the fatigue threshold of the interface can be increased from maybe 50 to 300. Now, it's a simple way to increase the fatigue threshold of the interface. And this design, we believe, is applicable to many different kinds of adhesion. For example, this adherent can be glass, metal, tissue, elastomeric hydrogel, can be any kinds of material, as long as it can form some chemical bonds here. And as long as you use this long chain polymer network, so the fatigue threshold of the interface will be very high. There's many different kinds of combination of different adherent. Okay. Another problem we need to solve, and we found in our experiment, is that when we define this fatigue resistant adhesion, because we use hydrogel here, when we use very long chains, so the first conflict, we call it a stiffness threshold conflict. Actually, there's another conflict, it's called the swell threshold conflict, because usually when we design this adhesion structure, this adhesion structure will be used in some liquid environment, for example, in human body or in some animal body tissue environment. So there's water around. So the water molecules will move in and will swell this interface and cause fracture, or at least reduce the fatigue property of this interface. So to resolve this swell threshold conflict, we follow the strategy of the double network design. So we introduce some microgel matrix. Actually, this microgel is also another kind of hydrogel. So this microgel is very stiff. So when we combine the 200 of hydrogel, the one is the long chain PEM hydrogel, another network is the microgel. So the microgel will provide stiffness as well as a very good swell resistance. So with this combination, we can simultaneously achieve a very good fatigue resistant property and also swell resistant property. So here's our experimental result. For example, if you use only as prepared PEM hydrogel. As prepared PEM hydrogel as an interface, the fatigue threshold about 200. But if you swell it, after swelling, the fatigue threshold will reduce about 1/3. But if we use this microgel matrix reinforced hydrogel, so we can see even after the hydrogel was fully swollen, the fatigue threshold still remains a high level. And this number actually is good for most of the biomedical applications, actually. So this is another demonstration of this long chain strategy. About the design papers, all these designs all these designs are used the long chain polymer, the long polymer chain strategy invented by my group, and also we can find some other group also use a similar strategy. Of course, Professor Zhigang So is our collaborator. So they use this long chain strategy and combine it with a high entangled polymer network. So it still need to resolve this conflict of toughness and stiffness. So when you design an elastomer, of course, we want to use a very long chain. And also we entangle it. So the long chain will provide toughness, and the entanglement will provide the stiffness. So it also resolves this toughness and stiffness conflict. So with this design, we can see this high entangled hydrogel with the similar toughness but much higher modulus or stiffness. So it's a similar idea to use the long chain strategy. And another paper from Professor Xuanhe Zhao's group from MIT, actually they invented some tissue adhesives, and the tissue adhesives that they synthesize has a very large value of interfacial toughness compared to the conventional the tissue adhesives. It's maybe 2 or 3 orders of magnitude higher. And they also claim that to prepare such high toughness interfacial adhesion tissue adhesives, they need to use very long polymer chains. So it's another example to demonstrate the long chain strategy to improve the toughness. This is the example in the tissue adhesives. Okay, so actually there's many other interesting work to develop the fatigue resistant hydrogels. So actually we only focus on the tough hydrogels or the double network hydrogels. Actually many other methods can be used to design some microstructures, like in all these works. They have designs of microstructures to improve the fatigue resistant property. Okay, so here's the conclusion. So we find that in a double network hydrogel, actually the sacrificial bonds will improve the toughness, but the chain length of the primary network will determine the fatigue threshold. So these two properties actually are totally different. And second, the relation between the chain length and the threshold accords with the modified Lake Thomas model, and we have performed many experiments to verify this. And the third one, we find that this long chain polymer network is a very effective strategy to achieve fatigue resistant materials and fatigue resistant adhesion. Okay, so for acknowledgement, so this work is collaborated with Professor Zhigang Suo from Harvard University, and these are my 2 PhD students, and the 3 are my colleagues, and Professor Hu help us a lot to synthesize hydrogel, and Dr. Tang help us to establish the method to measure the fatigue threshold of hydrogels. And all this work were done in the soft machine laboratory in Xi'an Jiaotong University. Okay, thanks all for my attention. Thank you.
Yeah, thank you, Tongqing, for the very interesting talk. And it seems you have basically do a very comprehensive study on the fatigue behavior of the hydrogel, the tough hydrogel. So with that, I think we can open our discussion with the audience. So if there is any question from the audience, please feel free to unmute yourself and ask a question directly.
So, Dr. Lu, I have a question about the toughness as a function of the length of the chain length of the primary network. It's this so that based on the observation you mentioned that the toughness is increasing with the chain length. So you use very long chain length, so you can get a very good the double network performance. Is there a plateau you can reach? For example, I guess it's impossible. You can continue increase the length and reach to better and better performance. Is there a kind of plateau, or there's a a kind of optimal chain length region you can reach to that high performance hydrogel?
Thank you, Dr. Lee. Actually, for example, when we do this experiment, we want to confirm that the fatigue threshold is proportional to the square root of the chain length. We have 5 data here. For example, your question is, can we further increase this chain length to get a even higher fatigue threshold?
Yeah.
So when our student, actually, my student actually indeed have tried such kind of experiment. When he further increased the chain length of this primary network, what they found is that the hydrogel is too soft. It almost looked like a fluid, actually. So that's leads to our next study, stiffness threshold conflict. So if you want to increase this fatigue threshold by simply increasing this chain length, the modulus will dramatically drop. Okay, so there's a conflict. So there's not a plateau, but some other limit for this material. Okay, so actually, when we do this experiment, the material we can see it just cannot be synthesized to form a solid. It's like just a liquid state. Yes.
Okay, thank you.
Hi, Tongqing. So in fact, I have many questions here. So first of all, since you are focusing on the fatigue behavior here, right? So and meanwhile, I believe you have also done some kind of stress like stress strain measurements.
Mm-hmm.
Right. So are you able to see the like a hyperelastic like a behavior from the simple tension or some kind of basic tensile test?
Oh yes, of course. The
That's it, right?
sprinters
Yes.
is highly nonlinear. Yes.
Okay. So here, so we see the high nonlinear behavior, like sometimes we see the hyperelastic. But I'm also curious here. So when we see this kind of nonlinear behavior, how we can tell the can we tell if there might be any viscous like a phenomenon here? Or how do you understand? Because these days I'm thinking, I'm still trying to understand the mechanical behavior of soft matter. So when we see this kind of hyperelastic large strain behavior, so how we can measure the viscous effect aside from the elastic?
Mm-hmm. Okay, thank you. Maybe Dr. Lee is an expert to measure the viscosity of the soft matter. So actually, yeah, there's like the machine of a DMA, like the dynamic mechanical analyzer. So such kind of machine or can measure the viscosity, some parameter, viscosity parameter of the hydrogel. So in for our material, actually. When we see viscosity, maybe you mean the rate-dependent behavior or the time-dependent behavior. So here, actually, when we study the fatigue, actually, we do not. For example, when we do fatigue, we need to fix a given frequency, the load frequency. So the low frequency, of course, will change the viscosity or the behavior of the material. When we do all these kind of experiments, the frequency is fixed in a very narrow range. So it means we do not actually to particular study the frequency effect or the viscous effect. But we can see that after many kinds of cyclic load, actually the loading and reloading curve almost coincide together. So the hysteresis actually is very small. So when we study fatigue, as we know, for many different materials like metal or composite polymers. So when we report, for example, the fatigue threshold or many different or many other fatigue properties, you need to fix frequency. You need to fix the frequency. So here we do not study the effect of frequency. Yes.
I see. I see. Yeah, that is good information to follow later.
Mhm.
Thank you very much for that. And my
Mhm.
another question, in fact, is about your peeling experiment. So
Yeah.
seems you have two, I'm not sure, clothes or fibers attached with together with each other at the beginning, right? So do you just kind of add the hydrogel in between, or so? I'm thinking for example, for your top layer and the bottom layer here. So in between, so seems you are putting in some hydrogels to make the adhesion larger. Is that the good correct understanding here?
Actually, when we prepare this kind of examples, we do the following. So there's the top layer of the cloth. This is it's like nylon. There's a nylon cloth. It is another layer. Actually, we soak these two pieces of cloth in the precursor of the hydrogel. So before hydrogel to become the solid state, it's liquid state, we soak them in the precursor and cross-link. So when we cross-link, of course, because the cloth has many holes, microscopic holes, so the polymer chains will penetrate into the holes, so it will form a adherent structure naturally. Actually,
I see.
yes.
So seems you can through the control of the network, either like a double link or through some kind of linker, so you can control the fatigue or the some kind of adhesion of the material. So with that, I'm just curious how you can achieve that control in your experiment. Like you use chemical, or you more like a different temperature, or different curling rate or something.
Actually, I'm not an expert in chemical synthesis, but as I said, yeah, there's many professors involved in this work, and they are material scientists. They know how to control the chain length, actually. So as I understand, maybe not quite expertise. So as I understand, to control the chain length, you just change the concentration of cross-linker. So because initially there's many monomers in the precursor. So add some cross-linker means they will form polymer chains. Yeah, if we put more cross-linker here, so the polymer chain will have very short. So if you have a fewer cross-linker, the polymer chain will be long. Of course, because this process actually is a random process, so we can just see in average the polymer chain is long or short. Okay, so actually the control the method of the change of polymer the chain length is simple. It's simple, but yeah, those professors, the material scientists, taught me how to do that. Yeah.
I see. That's very interesting. So yeah. Thank you very much for the further information. So I definitely learned something from here. So thank you so much. So with that, I'm not sure if we have more questions from the audience. So let me see. So if not, I think we can close our today's discussion here. And with that, we would like to thank our today's speaker, Dr. Tongqing Lu, again. And if the audience or the audience on the YouTube side may have further more questions, so please contact our speaker directly. And you can find his information from the website of the Xi'an Jiaotong University. So with that, thank you again, Tongqing, and let's keep our discussion after the meeting.